Work and energy. What is energy? Energy is a hard thing to define, but all the objects below have some kind of energy, even though we can't define it. And you'll see different charts on different websites and different books, but we're just showing this as an illustration. All right, you have a frog leaping, cars moving, ice cream melts, and we'll go all around the circle here. There's food, energy. There's nuclear fusion, which happens in the sun and in stars, nuclear fission, all kinds of different things, which is kind of funny because we can't exactly define it. However, in this course, we're only going to worry about two types of energy. Energy exists in different forms, such as gravitational potential, kinetic, chemical, sound, light, and heat. In this unit, we will focus on two forms of energy. First is kinetic energy. That is the energy of a moving object. Then, gravitational potential energy, which is the energy of an object due to its position in a gravitational field. Before we dive deeper into energy, we need to define a term, system. A system is the collection of objects that we are interested in. For example, our system might be one object, like a bowling ball. Or we can say that our system is a bowling ball and a bowling pin. Okay, and right over here, this is our system B, bowling ball and a bowling pin. This is just the bowling ball, system A. When we solve physics problems, we need to specify our system, the thing or things that we are interested in. Energy can be converted from one form to another. For example, gravitational potential energy to kinetic energy. We can do calculations with energy. Even though we can't explain exactly what energy is, we can say how much of it we have. Energy can be converted from one form to another. But can the total amount of energy that an object has be changed? Well, the energy of an object can be changed by applying a force from outside of the system. But this force must be applied in a special way, and that way is work. Sometimes scientists take a regular word and give it a special meaning that doesn't match what you think it is. If you're holding a heavy object, do you think you're working hard to hold it up? Of course you are, but in physics, if you don't change the energy of the object, you are not doing work. From a physics point of view, this athlete is not doing any work while she is holding the weights. Work can either increase or decrease the energy of a system. Positive work adds energy. Negative work removes energy. So in equation form, initial energy plus work equals final energy. And that's shown right here in this equation. Right here. E initial plus work is equal to E final, and work can either be negative or positive. If there are no forces outside of the system acting on an object, then there is no work being done. So work is equal to 0. Then our equation, E initial plus work equals E final, work is equal to 0. So you have E initial equals E final. The energy doesn't change. This is called conservation of energy. One definition of energy is the ability to do work. A rock sitting on the ground can't do anything. It has no energy. It has no ability to do work on anything else. However, a rock falling off a cliff has gravitational potential energy. Since it has energy, it can do work. If the rock falls on something, it would crush it. It would be able to do work on something. Consider this car. The children are applying a force on the car. How would you know if any work is done? Work is done on an object when a force moves the object to another position. Displacement is the change in position of an object. If an object moves from its original position, displacement is how far it has moved. These children only do work on the car when they move it to a new position on the street. As it moves, it has energy of motion, kinetic energy. If the car doesn't move, its energy doesn't change, so no work is done. If the object experiences a force and does not move, then there is no displacement of the object. It is not moved. No work is done. There must be an equal opposing force. The object is in a state of equilibrium. If the object moves in the same direction as the direction of the force, the work done is positive. The work is greater than 0. So what do we have here? We have our object, mass right over here. The force is in this direction, and so is the displacement. The force is doing positive work, increasing the kinetic energy of the object. The object will speed up as it moves to the right. If an object moves in a direction opposite to the direction of the force, the work done is negative. The work is less than 0. So in this case, the object has a displacement to the right, but the force is to the left. For example, if you give a box a quick push along a tabletop, it will eventually stop because of friction. The friction force and the direction of motion are opposite, right? So the box is still moving to the right, but friction force is in the opposite direction. The friction force and the direction of motion are opposite, so friction does negative work on the box. The friction force, is doing negative work, decreasing the kinetic energy of the object. The object will slow down as it moves to the right. If the object moves in a direction perpendicular to the direction of the force, the work done is 0. There is no work done due to the fact that no force acts in the direction of displacement. Right? The two forces acting are the force of the table, pushing the block up, and weight, which is gravity, pulling the block down. But the displacement is in this direction. No work is done by the normal force, which is the force of the table, or the force of gravity. Therefore, the energy of the object does not change. The amount of work done is calculated using the following formula. Work is equal to force times displacement, F standing in for force, and D standing in for displacement. Since work is the change in energy, it must have the same unit as energy. Work is force times displacement. The unit of force is the Newton, and the unit of displacement is the meter. So, the unit of work and energy is the Newton meter, or Newton meter. In order to honor James Prescott Joule for his contributions to the understanding of energy, the Newton meter is named the Joule, or a capital J. A 50 Newton force pushes an initially stationary block on a frictionless surface while it travels for 10 meters. How much work was done on the block? How much energy did the block gain? We have our givens over here, the applied force and the displacement, and we need to find work. So we use the work equation, put in our force, our displacement, and we get the work is 5,000 joules. 5,000 joules of work was done on the block. Now we want to find the final energy. We use the work energy equation. E initial plus work is E final. The initial energy is 0. The work is 5,000. So our final energy is 5,000 joules. So the amount of work done on the block is exactly the amount of energy gained by the block. This was the work. This was the change in energy, the energy gained by the block. The work done on the block becomes the kinetic energy of the block. It's moving.